Good morning, mathematicians. We're back to it. Oh, you can see I was trying to fix the stream delay. It turns out I didn't have stream delay enabled. So, yeah, nothing's going to change. I didn't think lag was that bad anyways. Obviously, at least one person disagreed, but here we are. I was trying to fix the stream delay. It turns out I didn't have stream delay. So, getting back to spectral sequences. Pop out the chat. I didn't want to see that. Where'd chat go? Top chat, live chat. Look at me remembering how to get set up. Okay. So, where were we here? We were looking at this guide to the spectral sequence. We had looked at the baby Hopf vibration and the bigger brother Hopf vibration, and now we're looking at this. Good morning, Lockheed. Good morning. Hope you're doing well. Good afternoon, or evening, I should say, to you, actually. Okay, so consider again the quotient map from Cn plus 1 to the n-dimensional space, projective, complex projective space. Wait a second. Wait just a darn second. Wait just a darn second. How are we... making this map? Why is it pairs of elements? Generalizing the Hopf vibration, consider again. Hello, Arad. The quotient map from Cn plus 1 without the origin to n-dimensional complex projective space. Wait, where are the pairs of elements coming from? Oh, should that be the real and imaginary part? No. Cn plus 1. Should n plus 1 be even? What's going on here? Maybe the pair is just referring to the previous example where n was 2. I suppose, but it seems like we're supposed to be going to general n here. And actually, like we did, there's a previous example and we sort of skimmed through the next example, or here you take the quaternionic projective plane, which again makes sense. You were reading a bit of Hatcher again the other day, and you notice that cellular homology, being the homology of homology, sounds suspiciously like the beginning of some sort of spectral sequence. Wait, cellular homology is the homology of homology? Oh. The proof of that is actually the beginning of the E2 of an E2 page. Okay. Did not know that. Did not know that. Okay. I mean, maybe that's just a typo, but definitely one can just take the... Yeah, wait. This should be a 2n. This should be a 2n, right? Because the natural map, unless maybe there's a different map going on here, but like normally... Oh, no, but then, right, okay, sorry. If it was the natural map, no, okay, because then the fiber definitely wouldn't be S1. Okay, so this is some other map that I don't understand. But yeah, this is weird. Then there should be... Okay, I think there's a typo here. This should be a 2n. This should be a 2n. I don't know how we're still missing a 1. Maybe this should be a triple of points, 1 for each n plus an extra complex number. Let's look it up. S1, S2n plus 1, CPN. CPN is a quotient of CN plus 1. Yes. Oh, so maybe, hang on, maybe this is actually supposed to be n complex numbers and the W is supposed to be the extra 1? Right. Oh, yes, sorry, you're right. Okay. Yes. CPN is a quotient of CN plus 1, which is R2n plus 2, and then the unit spheres. Okay. Yes. Okay. Yeah. Back on track. I still don't get what they were saying here, but it is the natural map up above. So that's fine. And then... So the restriction of the quotient produces a map from the sphere, over which the fiber is a point. Okay, not totally sure, or sorry. The fiber over point is S1. I guess it's basically just the same arguments as before. So we have a vibration. This will be our input for our first example that actually computes some cohomology that is not already assumed. Hell yeah, baby. Great. Although we will be running the spectral sequence in reverse. Arad told me this would happen. Well, this coffee's not bad. I got a new flavor. Not bad. To start with, we plot the cohomology of S1 on the vertical axis. Hello, Pajama Man. We plot S1 on the vertical axis. Why do we do that? Like, if you reverse the sequence problem, the problem becomes trivial by duality. That's what you've learned from chain complexes? I'm not sure I'm picking up what you're putting down. Okay, because here's the thing. In these other cases, we knew that things were tensor products. I think this comes back to my old confusion where, Arad, you were saying that the starting data always goes on the axes. I don't know why that's true. But maybe it's by the definition here. Right. Oh, it's by this definition here, just putting the zeros. Right. Okay. That's where it's coming from. Okay. Awesome. Right. So we have this picture. Nice. Okay. So where are we here? Start with plot the cohomology. Follows immediately that only the bottom two rows of the E2 page can contain non-zero groups. Because I guess if you go high up enough on the axis, you've got a bunch of zeros staring into these groups on the bottom two rows. Oh no, I mean it just comes from the definition again of the E2 page, right? Your hypercubing knowledge only gives you very vague intuition for S3. Yeah. Well, you're learning how to handle them today, Lockheed. You're learning how to handle them today. Okay. So from h star of S2n plus 1, the E infinity page will have a z in degree 0 and 1 in degree 2n plus 1. Porque. I guess it's the same computation that we did before. You trying to visualize a solution for that and being very upset in your first week. Yeah. Well, yeah. Yeah, how did this work before? What was the right. The E infinity page should be the tensor products. Is that's what it was? No. Wait. It was when there was no torsion. And there shouldn't be torsion here either, right? So shouldn't it all just become tensor products? And then how are we so sure? How are we so sure that the z's, like, because before we used basically the tensor product theorem to just say, oh, we've got these z's everywhere. And then from there we could see which would survive. So then why aren't we just using tensor products immediately here like we did in all of the other cases, though? Like, why wouldn't we just apply that here? Or do we need to know, does it need to be that there's no torsion in the cohomology of the whole thing? Because, yeah, when he said, or she, or whom, I don't know. Based off name was Jane, so I'll say she. I'm gonna take a guess here, and I'll correct me if I'm wrong. If you can solve 3 by 3 by 3, then you can absolutely have an attempt at 3 to the 4. You don't know how to solve 3 by 3 by 3? I don't know what that means. Lockheed, in terms of hypercubing and solving 3 by 3 by 3. One of these days, I've been sitting on this, on my own way of playing 4D chess for quite a while. And I've done it in such a way that you can play on a regular chessboard, actually. One of these days I should make a proper video explaining the rules of it. Really makes your brain hurt. The goal is to compute cohomology of the base space. So you're not supposed to know it yet. Sure. Oh, so I don't know. Right. So we don't know that the base space is torsion free. Okay, but still, am I correct in that when she says there is no torsion, where is it being said that there's no torsion? Does no torsion refer to there's no torsion in the homology of B and F? Oh, sorry. Yeah, it was clarified in the footnote, and we did even read that yesterday. Right, it's in B or F. Okay, awesome. We're back on track here. So, concise introduction to topology casually says isomorphism because epi and mono, without even mentioning to check whether that's true for groups. I mean, the book is called Concise for a reason. There's a lot of things it'll say casually, and a lot of things it won't tell you. Good book, though. So, okay. The claim, though, is that from here, the E infinity page will have a Z in degree 0. Why is that true? You do know that the question mark in 1I will be the tensor product of Z, and that's probably what you had in mind. Okay, let's see. Let's draw this. Why can't I go? Won't let me go lower until I start drawing. Whack. Okay, so we have Z and Z, and then a bunch of question marks. But then also, right, what is it? So we have E EST2 is HSB. So CPN valued in HTS1, right? Yeah. You have the money, you have the patience, you just don't have the dimensions. If anyone has the money and the patience, there is a physical 2x2x2x2 that you can buy to play around with. Lockheed, I have no idea what you're talking about right now. And what do you mean by solve? We solve way beyond 4D. There are records up to 70. What? I don't even know what you're talking about. Solve what? What are we solving? Quite confused. Why I say Lockheed instead of Leonardo? Both of us start with an L, but Leo's a turtle. Good question. But I mean, why not call? I like that you called him Locke. Maybe I'll start calling. I'll start referring you. Oh, you're talking about Rubik's cubes. Oh, I see. Hello, Fimno. Yeah, maybe I'll start calling you Locke. Also, because it reminds me of John Locke from the series Lost, which is another way that you know how old I am is the fact that I watched Lost. When it was coming out on TV, I saw episode 1. Okay. So... Right. Are there some other things that we can answer here? Well, right. So we already checked when S is 0. That this just spits out these two things. That's how we got that these rows are here. But how is it that we can determine literally anything else? Oh, because the claim is that this should converge to the homology of the sphere. Right. So we know that the E... Right. So we know that the nth homology... Or sorry, let me write it as like the ith homology of S2n plus 1, which is just going to be, we'll have z for I equal to 0 and 2n plus 1 and 0 otherwise, and that's the sum over s plus t equals n of e infinity s plus t. Your linear algebra prof did work on polytopes in dimensions greater than 3. Said she spent 9 months imagining the fourth dimension. We asked if he could do it and said kinda. I did apply for one postdoc position in Europe, in Sweden, to do automorphic. It involves automorphic forms and proof assistance. Yeah, I feel like in playing my 4-dimensional chess game, when I was playing it more often, I did develop an intuition, I think, for 4D. But yeah, it makes your brain hurt. Definitely makes your brain hurt. Okay. But what is calculus? Is it mathematical analysis 1 and 2? I would not say it is. Not in North America. Okay, so, but where were we here? So, what does that mean? Right, so the claim was that we know that this will have a z in degree 0 and 1 in degree 2n plus 1. Right. So we know that the s's and t's that sum to 0, and since they're non-negative, I think we have to have that z is e infinity. Oh, sorry, this should be s comma 0. So e infinity 0, 0 should be z. Right. E infinity 0, 0 should be z. The other one is maybe more complicated because it's going to be this big sum. But then there's also this claim about 0, 1. The claim is that 1, 0 is 0, though. Do we know for sure that 2n plus 1 is bigger than 1? Oh, yes, of course we do, because n is at least 1. Right, n is at least 1. So we know in particular that 0 will be the sum of e1, 0 infinity and e0, 1 infinity. So that implies that they are both 0. Nice. Okay. In Europe it is, yeah. Yeah, that's true. One thing you've always been interested in is a mathematician's take on higher dimensional games like 4D golf. I feel like 4D golf isn't that much different. 4D chess is very different, but 4D golf, because I mean, it's just like, well, I guess you got to think about how you're going to have gravity work. But you still probably want gravity to pull you towards a 2D surface. Maybe there's more to think about there. What's called analysis in America is usually called calculus in Europe, yeah. They learn measure theory before integration by parts. Hell yeah. Based. It would be interesting to see a mathematical exploration of projected 4D space in first person. Yeah. That gives me ideas. Guess it's not too hard to imagine singular geometric objects in 4D, but it'd be really interesting to be able to imagine a world in 4D. Yeah. Good morning, Tenacity. You hope I solved the Riemann hypothesis? I don't know if you should hope for that because I'm not working on anything remotely related to it. So if I accidentally solved the Riemann hypothesis, this would like we'd be living in a very strange world. Who knows? Maybe I'll change my mind and work on it. I would rather solve the missing Moore graph problem. To be honest, that would make my heart happy. These direct sums might be non-trivial extensions, but so if the extension is 0, then the... Wait, what? These direct sums might be non-trivial extensions? A new AI crank attempt at P equals not P dropped on archive? Is local Langlands the key to the Riemann hypothesis? I'm not so sure. On archive, there's a... What is it called? ABS. How do I... Where do I type that in? Okay, I'll just put it in Google. 2510.17829. It makes me... What? Is this it? How did this get on archive? This paper establishes the separation through a novel homological algebraic approach grounded in category theory. That first line already seems a bit sus. Triality and functoriality. I should click on that. That's real math. What? They associate chain complex to problems. I mean, points for creativity. I mean, I can't. There's nothing at the moment that makes it seem obviously. Oh, never mind. Yeah, I mean, this is probably straight from ChatGPT. Bold points. And claimed formal verification in Lean 4. Interesting. Okay, I mean, the rest of this isn't, I don't know, interesting. They mess up on theorem 3.14. Yeah, I mean, there's a lot of stuff I don't know enough about here to seriously judge this paper. But, interesting. They have a supposed formalization in Lean 4, but the repository does not exist. Interesting. Oh, Ben Feingold. Yeah, I used to be a big Ben Feingold fan. Not that I'm not a fan of his anymore, but I just, I don't watch as many of his videos. But I used to watch a lot of his videos from the St. Louis Chess Club. Yeah, I looked at the abstract of this paper last night, actually. I don't understand much about it, but seems cool. But this is, I don't know, maybe we should have a regular office hour soon. But this is supposed to be a Spectral Sequence live stream. Well, yeah. Things like that pop up in archive not infrequently. It does happen. Yeah, I should definitely be reading more of this paper at some point, but not today. We're here to talk about spectral sequences today. Okay, what time did I start? I don't know. I'm gonna have gotta have let's say 15 more minutes, absolute max. 9:15, absolute max. We cut it off. But yeah, maybe we have a regular office hour soon to break things up and to go through go read the triality paper. Let's see. Okay, yeah. So anyways, the E2. Wait, this means that. Wait, I just convinced myself that E infinity 1, 0 was 0. But why is E2 1, 0, 0? As there is no space... Okay, so we need to deduce this as a consequence. As there's no space for non-zero differentials in or out. Okay. You love the idea for a computation in Langland's stream? Oh, yeah. Yeah. Well, just a paper reading. So 1, 0, that's this one, right? And so we've concluded... we know that both of these are 0 on the infinity page. And let's see. So on the maybe I could put together the actual spectral sequences parts into one video. No. I would not. No. Way too much work to go through and edit it. What may happen is eventually, when I understand spectral sequences enough to apply them to some group cohomology, I may then use them in a video in my series on group extensions, but this is very far in the future. Okay, so let's see. On the E2 page, what's going into E01? That's what we're arguing about, right? Is E0? No, E10 is E10. Well, this will be E minus 1. So it's already something over here. E minus 1 plus 1, right? Because 2 minus 1, yeah. So it's this thing over here, right? So this is what's happening on the right, and then the other thing is below here. So these are going to be 0. And then what happens as we turn the page? Right, I guess we're still just going to be having zeros in and out as that gets cranked up, right? It's going to miss all the potentially non-zero terms. Right. So this has to be 0. Okay, I think I buy this explanation. I think I buy this explanation. And a similar reasoning should tell us that 1, 1 is 0. Okay. Makes sense enough to me. There is non-abelian cohomology. Yes, and I think that maybe, I don't know if I'm going to be able to get out a video on this by Friday. I think Friday I'm just going to, because this question comes up in other Discords and stuff, with people just asking the basic question of what is cohomology. So I think I'm just going to make a basic video on what is cohomology for Friday. And then I think I'm going to try to get up, I think I might start talking about the applications of extensions with non-abelian normal subgroup. I'm talking about cohomology there. And then I've also started thinking again about getting back to the categories of module series. So I think that's everything that's on deck right now. And AI inside a black monolith with mathematicians dancing around it is kind of your aesthetic. Hell yeah. Speaking of group extensions, is there some generalization of cohomology to non-abelian stuff? Yeah. Okay, and then from this, we're able to say something about 3, 0 for similar reasons. And then, I'm guessing based off of things that I expect this to, right, there can only be, I was just about to say this right as I read it, yeah. Because I already know that something should, I already know that this is what happens for a complex projective space, right? So basically, all the odd coordinates vanish, right? Nice. Nice. Yeah, I guess I should put these on the line or whatever, but very nice. Extensions with non-abelian normal subgroups equals yes, please. Yeah, it will be coming. Maybe in like 2 weeks, 3 weeks. I don't know. I just want to make sure I get all my notes organized and can explain it not terribly. N categories in cohomology, which connects and generalizes group cohomology to more higher algebraic notions. Let me just... Interesting. That's how you know you're scared. Good. Good. May math strike fear into your heart. Very cool. In addition, we know that the z at 0, 1 does not survive to e infinity. Why? Note that any dr for r greater than or equal to 3 going out of 0, 1 is 0, since it will point below the axis. So the only opportunity... So 0, 1 does not survive to e infinity. Why do we know that 0, 1 doesn't survive to e infinity? Oh, right. We did that computation previously. Right. And then, so the only, and then because the higher differentials just 0, the only opportunity to kill it is if this is injective. We also claim that it is also surjective. If not, E20, E320 would be non-zero and survive to E infinity, but this contradicts this. Thus, D2 is an isomorphism. Nice. Wow, this is great. This is fun, actually. Right, so this has to be, we have to have an isomorphism here. Very cool. That's the second time you literally take screenshots of Arad's recommendations. Nice. Yeah, Arad for the win. Okay, I actually don't want to read any further. I kind of want to see... I kind of want to see if we can work out... Do we get a similar... I wonder, do we get a similar thing here? Is it Z's everywhere? Do we get a similar kind of periodic behavior? Well, maybe not, because that kind of depended crucially on us knowing that this E infinity page dies. But actually, where does this show up? So this is 0. This is 1. This is 2. So, right. I guess we also know that 2 is, because this is an odd dimensional sphere, we know that this has to die. So that means that E202 plus E211 plus E220 all die. So right. And then I guess maybe we can do, and then I think, right, an entirely similar argument should tell us that, but we don't know in this case whether one of the question marks is a Z or not. Because we also needed that. Remember the question mark above Z on the E2 page is a tensor product of the Z in 0, 1 and Z in 2, 0. But I thought we didn't know it was a tensor product because we can only know it's a tensor product if the let's go back. Do we get a tensor product if we know? Because when it says we require at least one of these to be free, this makes it seem like to me that it's the entire ring. But is it only true? Are you saying that if we know it's true in certain degrees, then we know that we get a tensor product in those specific degrees, even though the other pieces may not be free and finitely generated? Where are we here? Kind of spoiled it for myself a little, but that's okay. To be precise, it's H2CPN and H1S1. The inner group is Z, so you're looking for H2CPNZ, and that's already appearing on row 0. What? That is without exploiting the tensor product shortcut? Huh? Okay. So this question mark is E2 to 1, which is H2 CPN H1 S1, which is H2 CPN Z. Right. And then we know that that is H2 CPN H0 S1, which is E2 0 2. Right. Right. And so then actually we should be able to play the same game. Right. Okay. So we get here. I see. And then okay. And then all of these same steps should keep going, and we should be getting a bunch of Z's. Nice. And we keep playing this game. Nice. Okay. Still wrapping our head around the relative homology groups. Fair. I think that's going to do it for today. We already went over what I said I was going to do by a whole whopping 3 minutes. So, take care. Have fun. Compute some spectral sequences. And I'll see you back here tomorrow. Q